word and recall how we worked out the exercises that were dealing with this confidence intervals. I think we went to 6.3 sections, so page 318. So I'm gonna add 30 to it. Oh, thank you. Yes, definitely. That's nice that you remember that. But anyways, so let us get 350, something like that, right? So we can always access these pages fast enough. And now we're going to see what else we did in that section. I don't think I gave you a quiz. We just played with the formula for confidence intervals. Let me recall the way it looked. It didn't look very attractive, but when you look closer, you start to notice that this is much better looking formula because it just has 4 letters in it that very familiar, and they determine the left side and also the right side of interval that we can produce to estimate the population average, which is called population mean. So that's so-called confidence interval. And the level of confidence usually is 95%, or sometimes 99%. It depends, and depends on the z-score. So let me use this formula, find the exercise that wants us to find that confidence interval. Let's say 23, the level of catenin. Whatever it is, we can find the average level of that nice stuff that comes from cigarette. And exercise number 23, we consider a sample of size 40. 40 people were studied, and the average level was 172.5. So I call it as a sample mean. We have sample, we can always calculate the sample average as well as a sample standard deviation, which is 119.5. So there's 2 things we have given. And now they want us to produce 90% confidence interval estimate. So when I have the confidence level of 90%, then I need to take a look at the formula, actually at the tables at the end, and see what z-score this determines. So I go to Triola tables, right? So usual procedure, selected first choice, and then normal distribution that has this little chart at the end of positive z-scores. We even had a quiz on that. So they say it's a 1.645 whenever you have a level of confidence of 90%. So I just get this right away. And we are ready to get the answers. So 172.5, I'm using this instead of sample mean in the formula above. Then 1.645, which is also multiplied by a fraction with a standard deviation, 119.5, divided by a square root from 40. So left side, and we already know that to get the right side, I just need to do pretty much same thing, but plus sign will be inserted. So let us do this. Scientific calculator. And now just need to carefully enter this and do this along with me, because maybe it'd be a good idea I ask you to try to calculate something with a calculator today. So it's 119.5, right? That we divide by a square root extracted from 40, just like that. So I got a left side. This is 1.41, etc. The other side I'm gonna find by changing minus with a plus. So I highlight the minus, delete it, and enter plus. So I don't have to re-enter all of these tedious little numbers. What for? You just added your calculations. So I use this online calculator. It's designed so you can added those numbers. So what I found is interval from 141.4 to 203.58, or say 0.6 approximately. So that's where the average for the population is. We don't know if it's 141 or if it is 203. Probably the worst case scenario, if you consume more of that stuff, it may not be very good, right, for the health. So the worst case scenario is when you get more. So probably 203.6 is what I consider as a average, because we always try the worst case scenario whenever we calculate this intervals. Why worst case? Well, if I prepare for the worst case, if it's a little better, well, then it's gonna be not that bad, right? So we can be kind of on the safe side. And that's the point. So we have this way to go, and now I'm gonna be well, just doing some more of this stuff. So let's see what else we can do here. And I'm looking at another kind of exercises that also appear in the same section that I deliberately skipped, that actually deal with analogous formula, but instead of subtracted that z times sigma over square root of n, they call this a so-called error. So they say, well, we may add or subtract the same exact expression that is called as error. And this error is exactly z sigma over square root of n. Say, why do they call it as error? Well, again, they may go by that number to the left or to the right, so they can like have a interval based on that so-called error. That's what they talk about. So whenever they want to find the sample size, they could utilize this formula by doing a little bit of manipulation. They can do some algebraic trick of clearing denominators and then divide by e. And then when they square both sides of this, they're going to get z squared sigma squared over error squared. So it's really the same exact formula. They just write n out of it. So what is going on? Why they need it? Well, remember, our goal is to always estimate the population mean. So that's what we're actually doing here. We find the interval, the left end, the right end. That's where we know the population mean will sit with a level of confidence 90%. So we're 90% sure that the average is on this interval. Well, in order to get that calculation, what we did, we took the sample of 40 people. And this way, our interval become very wide, from 140 through 200. If you get more people, notice that according to the formula, the square root 40 in denominator. So if you had square root 400 in denominator, then the error would be smaller. So the number you add and subtract will be smaller. So your interval will squeeze. So you will get better approximation if you work with more elements of sample. But that's time consuming, and that costs money. If you want to study 40 million people, well, you need to invest in that. You need to have people that help you with all that data collection and so forth. So they spend time, and you're paying for it. And that's why you can decide what's the least I want to invest, but still get a good estimate. And that's why we are interested in finding the sample size. So how many people do I actually need to consider in order to get good estimate? Because if you get a big interval from 0 to 1 million, well, what kind of result is that? You want to get a little bit better approximations, and that's the whole point of this process. So if you select so many elements, that will give you a good estimate. Like, for example, if they look at the so-called margin of error 3 pounds. So I'm looking at exercise 14. They say, I want to approximate it with standard deviation of error of 3 pounds. Let's say somebody is losing weight. Usually that could be the case. So you don't want to go by more than 3 pounds. If somebody gets 3 pounds gain, 3 pounds loss, you get somebody with 10 pounds gain, somebody with 20 pounds loss. So that's just too much of variance. You want to say, my pills or whatever people take make you lose 1 pound. Period. You take a pill, you lose 1 pound. So people buy this pill and they lose 1 pound. But if you say 1 pound plus minus 3, it means if it's plus 3, then you may actually gain 2 pounds, right? Because you lose 1 and you go by 3, so you could even gain. So you take the pill, you gain 2 pounds. Who needs that? So that's why people really want to get a error to be small. So in this case, they say, what if error is 3 pounds? The level of confidence is 99%. So you want to be pretty confident here. I believe that this corresponds to a z-square 2.575. I think you already had that on the quiz last week, right? If you have 99 confidence, check it out. It's here on the bottom, 2.575, remember. Okay, so, and also we have another number here that says standard deviation of 15. Okay, standard deviation is 15. So the question is, how many elements do I need to consider here in order to start calculating the average, say, weight lost? So it's not gonna be by 3 pounds away from the actual number. And it turns out it's just what I need here. Notice that in all of these exercises, they always give you enough numbers, so you could just plug them in your formula. So I plug 2.575 times standard deviation of 15, so I square it, and error, which is 3 squared, just like that. So you put this in your formula, and that's all you need in here, and you will get a starting point. How many elements you need to select in a sample so you can produce estimates. So let me multiply this 15 squared and then divide this by 3 squared. And I get 165 something. Look at this. It tells me how many people or elements in a sample I need to select, and I cannot take 165 point something people. What I take is 166. So we always move to the next place. And that's where you actually start the process. So that's the first stage in this, in all of these calculations. Whenever you want to get some type of research, you need to get a sample, right? If nobody already gave you the information, so you need to do it from scratch. So you get yourself a sample, and the question is, how many? Do I take 1 element or 21 element? Well, it depends on how close you want to get to the reality, and that's what this sample size is talking about. Let's do one more so we can better see what is going on. There are lots of various interesting exercises in here. So, for example, 31. You want to estimate the average pulse rate of adult males. So, looks like you can just measure your pulse, but is that the average? So, how many people do you want to select, and how close you need to be to reality? That's the question. So, you want to be 95% confident. Whenever they give us a level of confidence, we already know automatically that this tells us that z-score is something, and I believe it's 1.96. Of course, you don't have to memorize these tables. You could just take a look at it and see that 196, that corresponds to 0.95. So it's good to have it available, the tables, right? So please check out where's yours. So next, I have rate within 2 bits. What does that stand for? Within, that's a new word. And that's the error. So it could be by 2 more or by 2 less. And that's what we have here. And the question is, how about the standard deviation? So the question is, what is the standard deviation that I need to take? Because they don't really have it here. And looks like they didn't give it to us here either. So that's kind of odd. They say use the rule of thumb, but the question is, what is the sample? We don't have the sample. Looks like I got a little bit carried out because I didn't check that there is no information here. There is no sample here, and they say data set 1. I can actually try to find it online because, as you can see in this textbook, they should have the samples at the end of the textbook, but I don't think they actually have it here. They're just answers, right? Let me check. That's kind of odd. I wasn't careful. I know there are no data here. I just want to double check, make sure. Oh, there is a data set. Oh yeah, there are data sets at the end. Oh, great. See, it was different edition that didn't have data sets. So they say, look at data set 1. Okay, let me look at the data set 1. That's even more interesting because we never worked with these data sets. I always told you to skip them, but now we can actually take a look at that data set for a change. Why not? So they say it's the very first data set health results. So they're looking at the number of males here. It looks like they want to pulse rates. And notice that the pulse varies. Looks like I want to know the lowest and the highest. 60s, do I have any 50s? I see 56, and so far I had 88. Let me scroll it down a little bit. We have 56 and 88. Anything out of this range? 56, I see another 56, I see another 88. And it actually continues on the next page. How about that? So 88 I see here, and anything lower than 50, oh, 96, I see 96, great. 104, but nothing lower than 56. 124, beautiful. Okay, that's it. So the lowest end is 56, and the highest is 124. I believe that's what I saw. So they say, we're not going to give you a mean and standard deviation. Actually, you could calculate, just put the sample in your calculator. But what they say is a rule of thumb. Well, they say just break this into 4 pieces and find the difference. And that should be helping us. So the rule of thumb for the standard deviation, it should be a quarter of this range. So 124 minus 56, you break into 4. So why do they do this? Well, that's if you don't feel like calculating standard deviation. I wouldn't do this, but they say use a rule of thumb, so I can show you what this rule of thumb is. So we got this 124, so I put in parentheses, subtract 56, and then divide this by 4. So it's 17. So they want us to use 17. If you feel like you can calculate the actual standard deviation, but since I have 3 numbers already, I will use the formula. So z squared sigma squared over error squared. Right? So let us put these numbers in and get the answer. So 196 to the second power. Sigma, which is 17, that's what I just got from the sample, divided by 2 squared. So put this in a calculator and don't do the exercises with not enough information. But I think just do it for once is helpful to show that we can do pretty much any problem here anyways. Times 17 squared divided by 2 squared. So here's the number. I need to take 277 something males in order to be able to get this pulse measured. And we always go with 278. We move to the next value. Just like that. So this is what the section is talking about. Extra little formula. And as promised, now I'm gonna move to the section that was here before, to section 6.2. So that'd be the page 298. So we get like 330 or so, at 30 approximately. That also gives us analogous formula here for the error, but in a case when you have the proportion. So what is going on here? Well, sometimes it makes no sense to talk about population average. The good example is when you vote. So when people vote, what's the average number of people that voted? not what we're using. We say, what's the percent of people that voted? So for one candidate, 40%, for the other, 60%. So the second one, because more people voted for the other candidate. So we're looking for the percent or for the proportion. And notice that the formula here for the year is kind of similar, but it's not really identical. It's in terms of Z, but PQ over N. So I get a proportion from the sample. People say, since it's from sample, I put hat in it, like a bar. They like to put hat. And then we estimate in proportion for the whole population. And exact same formula as one above. So we get a subtract that Z, or on the other side, we get to add that Z times that square root PQ over square root N. So it's analogous formula for the confidence interval. And I guess we just need to care about using this formula in the exercises, as that's really all it is. So I think that these two formulas are very, very similar, these two sections. And of course, two formulas are very similar. So I just want to do a problem to illustrate that, like exercise number 13 here that says, if we have number of people 800, and if out of this 800, 200 was X, and then remaining 600, right, was not X. So in other words, P is 200 out of the 800. That's P. And the complement of it is Q, which is what remains, 600 out of 800. So that'd be a quarter. You can say 0.25 and 3/4. So it's 0.75. So these are P and Q. And then what you can do is find the estimate for entire proportion. So let's say you consider the sample of 800 voters. 200 voted for one candidate, 600 for the other candidate. But that's for this particular sample of 800 people. So they say, can you, with a 95% confidence, notice that confidence 95% is 196 z-score, isn't it? We just utilized it here as well, right? 1.96 z-score. Find the interval for the entire proportion. So let me do this. I say it's a P hat and that's a Q hat, right? Because that's from sample proportion, we estimate the entire population. So I go 196, and then I multiply this by a square root, 0.25 P, 0.75 Q, right? Divide this by sample size 800, like that. So I get one end of this proportion, then I put a plus and produce the other end. Let's do it. The quarter, 0.25. I want to minus 1.96 and times this by. Now inside the square root, I have 0.25. Please notice you just enter these little numbers. There's nothing tricky about it. The calculator does all the work for you. I say, why this is 800 in denominator, not over this one? Well, you multiply two numbers and divide by the third. If you don't like this way, you can always use parentheses, and notice you're going to get 0.2199 anyways. Just put parentheses here, and then your parentheses also here. So this way, you will get what you need. I just need to re-enter in order to do that, because I think I needed to okay, 75. Just to show you that it doesn't really matter. Divide by 800, so it's still going to be that same 0.2199. So the message is, it doesn't matter.
Okay.
So left hand is here for us. What about the right? Well, change minus was a plus. We already know it, right? So use this calculator. Advices always try to use this free Desmos calculator, because right away you can change and see it's in between 22% and 28%. And that's how I can estimate. So we considered 800 people. Of course, the sample should be good, because if you just concentrate on one particular group of people or in one particular area, it's not going to give you the estimate.
No, sweetheart, I'll give you dinner in a few.
About the other regions, right? That's why you really want to make sure that you select the samples correctly. Remember, we talked about this already. But if you selected a good sample, then you will always get a nice estimate. So we got a big thing calculated. We know everything about proportion for entire population. And that's the power of it. So I hope that you can see that these problems are in a way very, very similar. Why don't I do one more without making up the story, with just taking the exercise from the textbook. So how about number 31 exercise that says the drug testing that wants us also to produce a confidence interval. So I'm looking at exercise 31. So we have a 3.2% of 200 users, and want to construct that interval. So let us go for that. 3.2%. That's P. That's a percent. So if you have 3.2%, I need to write it as a 0.032. Remember, 3% is 0.03. There are hundreds. And the sample size is 221. So how about Q? How about 1 minus P? Well, let's subtract that 0.32 from number 1 and get Q. It's 968. This is my Q. If you want 99% confidence, we already know that's 2575, right? The z-score. 2575. So we're gonna get the left end of it as a P. P hat minus z times square root of PQ over N, right? To estimate the proportion. So let me enter these numbers in a calculator as usual. So let's put in he had. What is that? 0.032. That's my sample proportion. Z-score is 2,575. Then I have to write it here. And then I take a square root, right? Maybe I can do one side and you can calculate the other side. So 0.32 here times this by point, that's what I just found, Q 968. 68. And then divide by sample size 221. So this is my left side. And then for the right side, I'm going to do the same exact thing, but put a plus, right? 2,575, which is multiplied by that square root from 0.032. Denominator is 221, and that's multiplied by that same exact number, 968. Where can I squeeze 968? Maybe I can do it this way. I can say here, 0.968. So let me calculate the right end, and then you will calculate the left end for a little quiz. So let me just enter the numbers, point, and you can enter it right away for the other end. Plus sign, 2.575, and then a square root next to it, 0.032 times 0.968 divided by 221. So my right end came out to be 6%. So the question to you, how about the left end? How about if you calculate this expression and tell me what the left end of this interval for the quiz? So it's a calculation, a little exercise. Don't worry, just put this in a calculator. If you forgot how to find this calculator, here it is. I put it in the chat for you. This. So you can open exact same page as I just opened on your screen and see what the other end is. If you, instead of the minus, here put a plus. Instead of plus, sorry, put a minus, right? The other end means you need to replace a minus sign with a plus with a minus. So that's what the quiz problem says, right? Find the other end. That'd be all. That'd be our little quiz for tonight.